This last lesson in our last section of lesson 1, we are going to talk about weak acid-base equilibria. So again, all the Bronston-Lowry reactions that we are going to study in Chem 12 will involve the transfer of a single proton. This will be of. How do you decide which species donates the proton? Well, up until now, it's been whichever one can. So for example, if I asked you to write the Bronston-Lowry acid-base equilibria, which form when the following pairs of substances are mixed in solution, and you've got this H2CO3, which is your, I'm cheating, I think it's carbonic acid. H2, yes, it is my carbonic acid mixed with the sulfate ion. Well, this one's kind of obvious because this guy can't be a base, this guy can't be an acid, so this is the acid, it's got a proton to give, this is the base, it can accept it, right? Easy peasy. So if we did this proton transfer, we would say that the H2CO3 loses a proton and becomes HCO3 minus, and the HCO or the SCO3 is going to gain that proton and become SO3 single minus as well. So for the H2CO3, this is the acid, here's its conjugate base. And then for the sulfite ion, this is the base, and this would be its conjugate acid. Easy. But what if I was going the other way? What if I started with the HCO3 minus and the HSO3 minus, which are both amphiprotic? How would I know who's going to act as the acid and who's going to act as the base? Well, there's a rule. So amphiprotic species, again, just to remind you, are species that can act as both acids and bases. So as an acid, you'll find it on the left-hand side of your chart because they donate hydrogens. And as a base, you're going to find it on the right-hand side because it accepts. So HCO3 minus is one of those amphiprotic species. It exists as an acid and it exists as a base. And what we're going to do right now is just determine how do I compare its strength as an acid or its strength as a base on the chart. Well, let's split my screen again and bring up that chart. Okay, so if we're looking at HCO3 minus as an acid, you're going to find it on the left-hand side. So it's going to be down here because it's relatively weak, right, because it's already lost a hydrogen. And we're going to compare it to whatever they tell us to as an acid. So C6H5OH, C6H, oh, it's right above it. Okay, so there we go. This is phenol, okay, phenyl acid. So if I look at these two, okay, HCO3 is a weaker acid than phenyl acid, so it is a weaker acid. Oh, right. I was trying to save you guys writing, but I have a hard time just writing the word weak. Weaker acid than C6H5OH. Whereas if we compared it to the H2O2 or the hydrogen peroxide, it is actually a stronger acid. Okay, that's it acting as an acid. If we wanted to look at it acting as a base, we would have to find it on the right-hand side. On the right-hand side, HCO3 minus is written here. So if I wanted to say that HCO3 is a stronger or a weaker base than C6H5O73 minus, I'm comparing it to this guy. Now, for bases, the lower you are, the stronger you are. So this is going to be stronger, meaning that it is a weaker base than the C6H5O73 minus. That's a lot to say. Whereas if we compared it to the species above it, then it is actually a stronger base. Awesome. So this brings us to the question of, what if we did that reaction in reverse? What if I mixed these two amphiprotic species, so these two species that could act as acids and bases? How do I know which one's going to be successful in donating the proton? Well, you just have to ask yourself, which is the stronger acid? So what we're going to do is look for them both on the left-hand side. So we already have the HCO3 minus down here, and then the HSO3 minus is up here. The HSO3, whoa, that is not what I said. The HSO3 is the stronger acid, so it's going to act as the acid. So if we mix HSO3 minus with the HCO3 minus, and you'll notice we don't write states because they're all aqueous. This is going to be in equilibrium with. So if this is going to act as the acid, we're going to write its conjugate base. So we are going to lose that proton. So then this is going to act as my base, and it is going to gain the proton, right? So acid, conjugate base, base, conjugate acid, and that's the way it would go. But there's also a follow-up to this. So yes, this is the equilibrium equation, but this equilibrium is going to favor a direction. The general rule is that in a Bronson-Lowry acid-base equilibrium, the side of the equilibrium which has the weaker acid, so we're talking between this acid and this acid, will be favored. Or I like to prefer to think of it as the stronger acid drives the reaction. Okay, so in this reaction up here, I have two acids. I have this HSO3 minus and I have the H2CO3. The stronger acid is going to drive the reaction. So of the two, so my acid is HSO3 minus and my conjugate acid is H2CO3. Of those, which one's going to be stronger? Now I'm going to guess it's going to be my diprotic because losing your first hydrogen is easier, so it makes it a stronger acid. So if we look these up, we've got HSO3 minus, which was my stronger of my two amphiprotic acids, but now I'm comparing it to the H2CO3, which is right above it. So the H2CO3 is the stronger acid in this relationship, which means that I'm going to drive the equation towards the weaker acid, which means that the reaction favors the reactants. Okay, so let's practice just that skill, and then we'll put these two skills together. So in the following equilibria, predict whether the reactants or the products are favored. So we have to identify my acid on each side. So over here, I've got HO2 minus forming H2O2, so this is definitely a base. So that makes this the acid. So the HSO3 minus forms the SO3 2 minus, and so then this must be my conjugate acid. So of these two acids, HSO3 minus and H2O2, which one is the stronger acid? So again, HSO3 minus is here, and H2O2 is surprisingly weaker, right? Because it is diprotic, so you'd think that it would be stronger, but it's not. So in this case, my HSO3 minus is my stronger acid, so the reaction is going to favor the products. Okay, so now what we're going to do is put this all together. I'm going to be giving you two reactants. You're going to have to decide which one's going to act as the acid. Then you're going to look at the acid and the conjugate acid, decide which one's stronger and which direction the reaction is going to favor. So let's do this guy. Now this guy's nice because it's not amphiprotic. This guy's amphiprotic, but that one is not. So this obviously has to act as my base, which is going to make this guy my acid. So that's going to form CO3 2 minus. And then I'm going to have an HSO4 with a single minus. And so this is my acid in my reactants. My acid in my base is going to be this guy. So I'm looking to see who's stronger. I think we already know the answer. So HCO3 is down here. HSO3 HSO4 minus. Where's that guy? So HSCO3 is down here. HSO4. Oh, he's way up here. That is definitely the stronger. Whoops, sorry. This guy. HSO4 minus is definitely stronger than HCO3. So HSO4 minus is definitely my stronger acid. So then my reaction is going to favor my reactants. So the first thing you're asking yourself is, am I dealing with amphiprotic species? So to answer that, you're going to look at HNO2. HNO2 has a hydrogen, but it doesn't have a negative charge, so it can't be amphiprotic. Water is amphiprotic. So what we have to decide is, what is the HNO2 going to do? Because it doesn't have a negative charge and it starts with a hydrogen, it's going to have to act as my acid. Oh, sorry, I'm in eraser mode. Acid. Which means my amphiprotic water has to act as my base. With the HNO2 acting as an acid, it's going to donate its proton, so you lose the positive hydrogen and gain a negative charge. Then the water is the thing that's going to accept that proton and become H3O plus. Then what we're going to look at is in this species, which side has the stronger acid. So the HNO2 is my acid, and then the conjugate acid of water is the H3O plus. So out of those two, which is the stronger acid? Well, we know that H3O plus is the strongest acid that can exist in water. So we've got the H3O plus, and then we're comparing that to the HNO2. HNO2 is down here, so definitely the H3O plus is going to be the stronger acid, which is going to mean that the reaction favors the reactants, right? The strong acid drives the reaction towards the weaker acid. So CO3 2 minus and H2S, which one's going to act as the acid? Well, this guy doesn't have a hydrogen to give, so this guy is obviously going to act as the acid. So the CO3 2 minus is going to accept that proton, and the H2S is going to lose the proton. So on the reactant side, the H2S is my acid. On the product side, the HCO3 is my acid. And if I lost it. One sec. I keep closing it so I can get rid of all the pencil marks. Okay, so which is the stronger acid? So we've got H2S. Where's my H2S? There it is. And then I'm comparing that to HCO3 minus, which I kind of missed my pencil marks because I definitely already had that one circled. So the H2S is the stronger acid. So I am going to favor my products. Just as I said, I was having a hard time finding ones that favored the products. Okay. At some point, you guys can always ditch me and start doing these on your own, but there are some with tricks. Okay, and the next one, we've got ammonia, which looks like it could donate a hydrogen, but it's actually not going to. Okay, so the ammonia is going to be down here. It is not able to act as an acid, which means this guy is going to have to act as my acid. So the NH3 is going to act as the base, so it's going to be form NH4 plus, and then the water is going to give that proton and become hydroxide. Okay, so we are going to look at which of these is the stronger acid. We're comparing between water and ammonium. So we've got water way down here. We've got ammonium right up here. So the NH4 is going to be my stronger acid, and that is going to favor the reactants. All right, the next one's amphiprotic. So for this one, you have to look up which of those amphiprotic acids or species is going to act as the acid. So how are we going to decide? You're going to look them up on your formula sheet, right? And you are going to find H2PO4 minus as an acid. So H2 should be somewhere. I found the 8. There it is. So there's my H2PO4 minus, and I'm comparing that to HSO3 minus. HSO3 minus is the stronger of the two acids, so it's going to act as the acid, which means this guy's going to act as a base. Acting as a base, it's going to accept a proton and become H3PO4. The HSO3 is going to give up its proton and become SO4 2 minus. Sorry, not SO4. It's sulfite. SO3 2 minus. Now, the conjugate acid of that base is this guy. So then to see which reaction is favored, I have to see who's stronger, H3PO4 or HSO3 minus. I'm going to guess it's H3PO4. There it is. H3PO4 is way up here. HSO3 minus was way down here. This is definitely your stronger acid. So H3PO4 is definitely my stronger acid. So my reaction is going to favor the reactant. Okay, last guy down here, I threw on because the textbook had some of these, and I was like, oh, okay, what happens with this? So this is NH4F, and it's not combining with anything. So what you have to do is you have to ionize this guy first. So this guy would break up into ammonium as a polyatomic cation and a fluoride anion. And then these are the two species we're going to mix together. So we're actually going to be looking at ammonium with fluoride. Now from here, there's no choice who's the acid. They are not amphiprotic. So this guy's going to be the base, and this guy's going to act as my acid. So the NH4 plus is going to donate a proton and become NH3. The F minus is going to accept that proton and become HF. So then my conjugate acid is the HF, and then I'm looking up who's stronger. NH4 plus, which we already said was down here, versus the HF, which is way up here. The HF is definitely the stronger acid, so my reaction is going to favor the reactant. Awesome. Okay, I think that is the end of this lesson. Perfect. Give that stuff a go.